Okay, I've got an example up here on the board of a work problem. I want to know how much work against gravity is done by a 150-pound person who's carrying a 30-pound box up a spiral staircase. The staircase is going to go up 20 feet and it's going to make one full revolution. Now notice I've specified that we're just talking about the work against gravity, so we're just talking about the vertical work that's being done. So essentially, if I were to get the force field, now this is a problem in 3 space here, okay? Gravity acts down, the person is going up, so the person is countering gravity with that. But if it's the work against gravity, I'm just concerned with the z component here. There really is, I don't fight gravity by going this way or this way, I fight gravity by going up. And, important to know, the force to lift an object is just the weight of that object. So, this person is carrying him or herself and the 30-pound box, so this is going to be 150 plus 30. Okay. I would remind you, if needed on an exam, that the force necessary to lift an object is just the weight of the object. Okay, so that is 0, 0, 180. Okay. Now, I'm going to need to parameterize my staircase, so let's go with an r of t. And if it's a spiral staircase, I'm basically going to be using the x and y components here to create a circle, and the z component to go up. Okay, so I'm going to try just a cosine t, sine t, k times t. Okay, now what that's doing is we're drawing circles in the xy plane, but as we draw them, we're going up, which is what a spiral staircase does. Now, I happen to have made it so that we're going counterclockwise. For this particular problem, that's not going to be relevant because, of course, I'm going to be dotting things with this force vector, and the x and y components are going to cancel each other out. Okay. But what is important is I need to figure out what this number k is. So the idea is we're supposed to make one full revolution by the time we're at 20 feet. So I want kt to equal 20 when t is equal to 2 pi. Because if I start at time 0, I would have made one full revolution at time 2 pi. So k times 2 pi equals 20. K would equal 20 over 2 pi, which is just 10 over pi. So I can say r of t is cosine t, sine t, 10 over pi times t. Okay, so we have parameterized our path. We've got our force field. So we are ready to set up our integral. So I know that work is going to be the integral along C of F dotted with T ds. That's just force dotted with displacement. But of course, the way I evaluate that is I'm going to be integrating, and I probably, when I parameterize this, should have included that T is varying from 0 to 2 pi. So we'll be integrating from 0 to 2 pi. It's going to be F evaluated at r of t dotted with r prime of t dt. Now, in general, when I switch from a ds to a dt, there's a scaling factor involved. Remember, the scaling factor here is the magnitude of r prime, but the magnitude of r prime is the denominator of the unit tangent vector. So when I switch from the normalized derivative, r prime normalized, to just the non-normalized derivative, r prime of t, that's canceling out that scaling factor. So it's not that there isn't one, it's that it's there, but it canceled. Okay. All right, so this will be the integral from 0 to 2 pi. My force vector, well, it was all constant, so it's just going to stay 0, 0, 180. I'm going to dot that with r prime of t. Now I've just written down r of t here, so let's calculate what r prime of t would be. That's going to be negative sine t cosine t. Here's the important part, 10 over pi, and then dt. And of course, the reason the important part was the z component is because now I'm going to do that dot product. And if I do the dot product, the x and y components of r prime here are just going to get canceled out by the zeros. So I get integral from 0 to 2 pi of nothing plus nothing, plus 180 times 10 over pi, so that's 1800 over pi dt. Oh, this is lovely. That's just 1800 over pi times the length of my interval, which is 2 pi. That's going to cancel. I get 3600. Okay. For this particular problem, we were measuring force, which was weight, in pounds, and we were measuring distance in feet. So the units for work are actually just foot-pounds. Okay? They really are literally just the product of the units that we have for force and the units that we have for distance. So, okay, there we go.